Welcome, I'm Tim Sever, and today we're going to look at a few examples of derivative rules by our established theorems. And let's go through them quickly. This is what's called the power rule. This is the sine rule. The derivative of sine is cosine. The derivative of cosine is minus sine. These are two technical theorems which says that the derivative of a scalar multiple is just a scalar multiple of the derivative, of course, provided the derivative of g exists. And this says that the derivative is a linear operator. The derivative of the sum is the sum of the derivatives, and the same holds with the minus. The derivative of the difference is the difference of the derivatives, provided both derivatives exist at x. Okay, so let's look and see how these are applied to this problem. Okay. So this rule says we can, when considering the derivative of this sum, I can take each piece separately. I can formulate the derivative of this piece and this piece separately to find the derivative of f. Okay? Now, the derivative of 3x to the fourth, since I'm looking at them separately, I'll do them separately. This piece first, then this. So the plus here, I'm just writing it here for effect. So now the constant rule says I don't have to worry about the 3. So in here, I can put the derivative of x to the fourth using the power rule. So what is the derivative of x to the fourth? Well, it's 4x cubed. Okay. So I've completed the derivative of the first term. Now, the derivative, it's not up here, the derivative of a constant is 0. So the derivative of 5 is 0. Okay, computed separately. Finally, what do we have as our final answer for the derivative? 3 times 4 is 12, 12x cubed. That's the derivative of 3x to the fourth plus 5. Okay, now let's look at the second example. Well, we don't see, at first blush, we don't see a derivative rule for the square root of x. Clearly we can do the derivative of x squared similar to the manner in which we did the derivative of x to the fourth. But we can rewrite the square root of x exponentially, well, with an exponent. The square root of x is x to the 1/2. Now we can, again, do the derivative here piecemeal or separately, looking at the two pieces or terms. And underneath, I'll write it h prime of x. What's the derivative of 5x to the 1/2? Well, the derivative of x to the 1/2 is 1/2 x to the 1/2 minus 1 by this rule. You could think of it as the n comes down, recopy the base of x and subtract 1 from the exponent, precisely what I did here. 1/2 comes down, recopy the base, subtract 1 from 1/2. Now the 5 is just out front. It's constant via this rule. So the derivative of 5x to the 1/2 has been computed here. Plus, what's the derivative of x squared? What's the same power rule? 2 comes down, recopy the base, decrease. Okay. So finally, in terms of the last step, let's see what we have. We want to do the simple arithmetic of 2 minus 1. Of course, in 1/2 minus 1 is minus 1/2. But I want to simplify this product here. So this is 5/2 x to the minus 1/2 plus 2x. All right. Now, that's finally the answer to that derivative problem. Okay. Now, again, we have for the third problem at hand, we have 3 terms, 3 cosine x, 5 sine x, and 2, or negative 5 sine x, depending how you consider things. But we have 3 terms to the problem, so we take the derivative of each term. So now I'm going to kind of skip the step of writing the 5 out front. Actually, I won't. I'll just skip it here. 3, what's the derivative of cosine? Minus sine, by this rule. What's the derivative minus, you rewrite by this rule. The 5, of course, you recopy 2, it's constant. What's the derivative of sine x? It's cosine x. And the derivative of 2, of course, is 0 because it's constant. So finally, this case, what's the answer? Well, the answer would be negative 3 sine x minus 5 cosine x. And that's the answer to that derivative problem. Okay. Now, Here, later in the course, we'll have a quotient rule. So here we have a rational function, but it's the quotient or the ratio of 5x minus 1 to x squared. We don't have a rule. There's no rule here to handle this, but we can do this problem by doing algebra. No derivative is taking place yet. I can separate this out as follows. I can simplify by canceling. Now this is not functions that agree at all but one point, but x over x squared does simplify to be 1 over x. All right, so our simplified form of this problem is 5 over x minus 1 over x squared. Now we want to rewrite this one more time for the sake of the derivative. That's 5 to x to the minus 1 minus x to the minus 2. Now we'll take the derivative of the function in this form. Why? Because you see it's written with two exponents, so we can apply the power rule twice. So the derivative of this is 5. Now that's just recopying it from the constant rule. Some of this you can do mentally. If you can do, and eventually you'll be able to, when you bring the negative 1 down, you'll write this as a negative 5x to the minus 2. I'm just putting in the steps to illustrate what's going on. And I've forgotten, while speaking, part of the problem. Okay, so now this is the derivative of x to the minus 1 is minus x to the minus 2. Recopy this minus sign. And in this bracket, I'll put the derivative of x to the minus 2, which is minus 2x to the minus 3. And you can see in this problem, notice I'm starting to simplify some of the steps. I'm not writing out the subtracting 1 from the exponent. I'm doing that mentally. Minus 1 is minus 2. Minus 2 minus 1 more is minus 3. So now all I have to do is the final simplification of the arithmetic. Minus 5x to the minus 2. Negative times negative is positive. Plus 2x to the minus 3. And we handled that product quite easily because the denominator was a monomial. There was only one term in the denominator. Had this been x squared minus 3, we could not have used this technique. Okay. Now, this may look like the power rule, but really you see there's an inside function here that's not x. So really there's a composite function happening here. We don't really have a rule to handle that yet. We will. That rule will be called the chain rule, but we don't have it yet. Certainly not one of the rules I'm demonstrating today. So what we want to do is just multiply this out, distribute. So we know the expansion for the binomial. No derivatives taking place. This, of course, is just algebra. All right, so I've expanded, I've squared 3x minus 1. We could take it, write it times itself twice, and do the expansion there. I just did it mentally. And so now, finally, the derivative of this trinomial will be taken in each piece separately, as we did here. Here, I took the derivative of each piece separately, and here. Here were 3 pieces, in fact. So I'll take the derivative of this piece, I'll take the derivative of this piece, and I'll take the derivative of that piece or term separately. Okay, so now I'm going to kind of skip the steps that I didn't do here. Let's review a little bit. I could have come back and said, all right, minus 1 times 5 is minus 5, minus 1 more is minus 2, minus 2 times minus 1 is positive 2, and of course minus 2 minus 1 is negative 3. So some of us, and you will be able to go from here to here immediately. That's what I'm going to do at this step. So you can see an application where I skip the rewriting of the simple algebra. So 2 times 9 is 18. So this is 18. And when I subtract 1 from 2, I just get 1. And we normally don't write a 1 as an exponent, so just 18x. Now here, the derivative of x is 1, so this just becomes minus 6. And you could see that via the power rule if you like. And what's the derivative of any constant? 0. So this is the, I'll write that step. So now for the final simplification to illustrate the derivative of that term, the answer is 18x minus 6. And there's the last derivative of the 5th example for today. Very good. Notice one last comment before we end the video. We're using these theorems. These are all theorems. They all can be proven. That's why they're a theorem. We didn't do the definition with the limiting process as I did in the last examples. So this is the way we'll be working problems as we go forward. You will be required to demonstrate your ability to work with a definition. That's not what we were doing today. Today we were looking at applying these theorems to solve these derivative problems. Thank you.